Just the time this is set up, let me introduce the speakers. So, last 3 days, you hear this development of the particle physics, and one the theoretical side, and on the detector side. But there is another front also there. The accelerator also developed.
It's working. Yes.
And based on the accelerators, you have a different kind of an environment, different kind of a detectors. And this accelerator first started with this collider experiment, fixed target experiment, beam hit on a material, some particle produced, we studied that. Then it come to this E plus E minus machine, that electron positons collide, and that the physics are there, that is also low energy and also this high energy, let's say 100 GeV center of mass energy. Then there is a machine where mainly for the deep elastic scattering, there is a HERA machine, electron or positron heated with this proton beam. This is the third kind of collider experiment. And fourth, as you know, that LHC experiment, this is the proton-proton collides or proton-antiproton collide, there is a collider experiment. And with all this, I talked of the fixed target, E plus E minus, low energy, high energy. This is the HERA, there's electron and proton collision, 5 different kind of detectors or environment. And there's the 5, for that 5 different kind of environment, there is 5 different kind of detectors is required and different environment also there. And now the next speaker, Professor Sridhara Dasu, he is the person who worked for all these 5 different kind of experiments. Starting from this, his PhD in this fixed target experiment, then he moved to this SLD, JUICE experiment, Barber experiment, and then now in the CMS experiment. And so you can understand that this physics depth and the detector depth, but only just in short times in the CMS, in his last many years, he's coordinated many of the physics group, but one of his passion or his main target or he spend most of the times is the development of the trigger and maintaining the trigger, upgrading the triggers. So then you can realize that is the appropriate person who can give you a talk on the trigger and the ecosystem to you. Okay, Sridhara.
Thank you, Govinda. Indeed, I did work on lots of experiments. They all sort of need trigger, but it turns out that the LHC trigger is almost everything that determines the physics capability of the experiment. So I think that it's appropriate to focus almost entirely on the LHC in the context of trigger. Even within LHC experiments, LHCb experiment got rid of the trigger electronics part. They still have a trigger in the higher level analysis phase, but most of the trigger electronics is gone from the LHCb experiment. That's because of the technological improvements that the telecommunications and electronics industry has made over the past many years. Long ago, high energy physics used to be a major player in development of electronics and trigger. Now we are power users. We use the best electronics that's available at any particular time, but we're really users. So we need to know how to use it more than we're not actually developing FPGAs, which I'll talk about, field programmable gate arrays. We're not developing high-speed optical data transmission lines. Telephone companies and their suppliers do that. So we're just using them. But we use them in a very, very strange context, which most of the industry does not even appreciate. So we're taking their devices and configuring it for our purposes. And our purposes are dictated by physics issues like what Amoldige talked about, coupled with the detector issues that Danielle talked about. I think this is the right place to go with this. And in particular, I heard that you didn't hear too much about calorimetry yet. Professor Banerjee will talk about it after I do. So my examples are all in calorimetry. So it will actually help from that point of view. I will talk about a little bit of tracking-based trigger in the next lecture. In this lecture, we'll focus on the calorimeter-based trigger primarily. I'll do touch on other aspects of the trigger as well. So that's what we'll talk about. So I understand from earlier when people raised their hand for a single question that there is a wide spread of expertise in the group of people here. So I have slides here which just repeat the same theme again and again. This is the entire theme for the talk, right? So the trigger is to select the interesting physics events quickly. That's a very important thing. Quickly is very important. There's no point in waiting for 65,298 seconds to select an event. There's just not enough time at the LHC to do that. So we have to do it really, really quickly. And we can't use all the data either. We have to use partial data. So I chose all those words for a good reason. It has to trigger, which means it needs to initiate something. And it needs to initiate something on every interesting event. I didn't say anything about uninteresting events, but it turns out that most of the events are uninteresting. The interesting events are few, but we have to trigger on interesting events. And we need to do it quickly. I'll define what quickly is. And you need to do it using partial data. So that's the trigger purpose. The second aspect is data acquisition, where we want to store the complete data so that we can analyze it with the full power of all the wonderful detectors that we have built. So we have to store the complete data for detailed processing offline. So that involves huge amount of computing. That can take as long as it can. So you can get PhDs. It usually takes 5 years to do an analysis. So this is the same thing in another slide. So you have the detector, which I didn't talk about. It produces data at a petabyte per second. That's a huge amount of data. A petabyte is not a small number, right? I just bought this computer just a little while ago. It has a terabyte drive, right? And we're producing a petabyte of data every second. That's 1,000 computers like this will be filled every second. You know how slow it is to work with a computer and download a movie. So what we need to do is get that data out of our experiment at that rate, a petabyte per second. Obviously, you don't want to store all of that, right? If you have a computer like that, you can store a few movies, not a big deal. But if you want to store that many movies continuously, that's not very productive either. Then you won't have time to watch them in your entire lifetime, right? So you watch them in the sense that in order to analyze them. So you need to somehow select only the interesting ones. So you only watch the movies involving favorite actors and actresses, but you discard most of them. That's very easy to do in movie world. And it turns out that's the case in particle physics as well. What is uninteresting depends on time. When I started my career, we were measuring deep elastic scattering in a fixed target experiment. QCD was most interesting. Now I define QCD as uninteresting. We'll throw it away. It's not uninteresting for everybody. And we also have an energy issue there in the sense that low energy QCD, maybe not interesting. Very high energy QCD or producing 10 jet events, the rate at which they're produced, it's still not very well understood. So we do want to keep some interesting events even in that case. On top of it, you also have huge amount of backgrounds which are produced because the particles which are produced decay. Many of them decay into leptons, and the leptons are interesting ones. So we want to keep those. So there's some good in keeping the backgrounds as well. So we have to do that. So we don't want to select only the Higgs event and throw away everything. Then we'll have, in principle, very little data. So we do store quite a bit of data, including backgrounds, and that gives rise to petabytes per year. That is something which Danielle was earlier referring to as a big problem of our begging with the funding agencies every year, because a petabyte of storage costs quite a bit of money. And we have to store that data every year. So every year we have to go with our begging bowl asking for funds. Eventually, though, people learn about it in some Twitter, which is one line of sentence, but it takes a lot of effort to get there, and we'll do that. So just to quantify it a little bit, so I've already given the full lecture in 2 slides, but now I'll go in a little bit more detail 3 times. This is just like any physics course, right? When you're taking physics, you do it at high school, you repeat the same thing at 12th grade, you do the same thing in bachelor's, you do the same thing in master's. That's what it is. So that's what I'll do here. So LHC had 2 runs so far, and the 3rd one just started. Run 3 and run 2 are almost identical, except for maybe a slight increase in the number of events that you get per second. So at the LHC, what we're doing is colliding proton bunches on proton bunches. Each bunch has got almost 10 power 10 to 10 power 11 protons in one bunch, and we're colliding them, and 2.5 10 to the 11 protons in a bunch, and we're colliding them. And these collisions are happening at 32 megahertz, 32 million times a second, right? So that's a lot of collisions. And anytime these bunches pass through each other, it turns out that multiple protons interact with each other. That's what Danielle called pileup. So we typically get 50 interactions these days in our at the intensities we are colliding. How do we get that many collisions? Well, I drew this bunch here with a very diffuse set of dots there, but the bunch is very clustered, very, very tight. And the tighter it is clustered, the smaller the emittance that you have of the beam, the higher the rate of collision. And we want the rate of collision to be very high so we can detect rare processes. So in these collisions on the order of 10 to the 16 collisions were collected in the previous run, which is a 3-year run. And out of that, we've made about 10,000 or so Higgs bosons. Okay. So in principle, if you're only interested in Higgs physics, you only need to keep 10,000 events. That's something that you can put on your pen drive and take it with you. But that's not what we did. What we wrote is a lot more events. We wrote a petabyte per year, so 3 petabytes of data was written down because we want to do more than Higgs. So in that 3 petabyte of events, which are represented by these bales of hay, it's actually underrepresentation there. You need to find that Higgs event, which is buried in there in those many bales, and we need to do it at the trigger level in this as soon as possible context. So to just set the scales, like selection of one event in this one followed by that many zeros, which I don't even want to count, right? So how do we do that? Why is it so bad? It turns out that it's even worse than you think. The reason is, in order to do the full detailed analysis, you need to have these tracks reconstructed. You saw these particles coming out. Every interaction of protons at 13 TeV in the center of mass produces on the order of a few hundred particles. Not every one of them is high enough energy that it will make it through the detector because we have a 4 Tesla magnetic field. So it'll curl up the low energy particles. They just go somewhere. Many of them also hit Sunanda's detectors, which is a nightmare for him to deal with in the forward regions. The multiplicity is very large of the small low energy particles. But the tracking and other detectors in the central region are see few events, but from each collision. But there are 50 of them. If you put them all together, the multiplicity of charged particles and neutral particles, photons primarily in the decays, is on the order of 1,000 particles per event that are. So those 1,000 particles are going through the detector, through this magnetic field, bending and hitting the calorimeters where they're depositing energy. All the photons deposit their energy entirely in the electromagnetic calorimeter, which in the CMS case is made of these crystals. And so the showers look like that. There are 80,000 of those crystals. You need a lot of crystals in order to find these 1,000 photons, which are distributed all over. And that's followed by a hadronic calorimeter. So if it's not photons, but if it were charged hadrons, they produce a little bit of energy here and some energy in the back of calorimeter. So you need to measure those very well as well. But even more importantly, you have these detectors here to track these charged particles. The charge content is about 2/3 of the particles. And that's a lot of 1/3 of the particles. So you get a lot of particles in there going through this tracking volume. So you need about 10 power 8 typically diodes, which this silicon strip detectors and the pixel detector, which is not even shown in the picture here, are made of. So you can't possibly, so each of them, even if it produces 1 byte of information, right? That's a lot of information to take out. If you say that I only read the crystals which have a hit in them, that would require some kind of a trigger. It could be a self-trigger. I have some energy in me, so read me out. People can raise their flag. If you just read that out, and your volume of data will be small. However, there's a problem. You need to know where it came from. If you have 10 power 8 sensors, you need to know which of the sensors. The identification of that sensor itself will take a lot of bits of data. So the amount of data that you get adds up to about a megabyte of data. So if you are reading a megabyte of data at 32 megahertz, that's a lot of data. That's what gives rise to that petabyte per second data rate, which you need to handle. So it's worse problem than you can think. So why is the rate so high? So I'll repeat now from physics point of view why the rate is so high. The rate is so high because proton-proton inelastic interactions. That means that two protons come in, out come more than just two protons. If two protons come back, that's the elastic collision. We'll just forget about the elastic collisions, as Danielle was saying earlier as well. We talk about only inelastic collisions that we're interested in. And the inelastic collision cross-section is about 70 millibonds or so, depends on how you exactly define it and all of the detail. So that amounts to about gigahertz. That's 10 to the 16 events per year. So that's a huge rate. That's gigahertz rate. But we are clocking the detector at 40 megahertz rate, so every 25 nanoseconds. Every crossing is not populated with data. 32 out of 40 are populated with data. So if you take that rate, that sits around 32 megahertz. That's somewhere here, right? This is a megahertz. So that's 100 megahertz. So that rate is sitting somewhere here. And if you look at it, that rate is about the same as about BB bar production rate. So for CMS and Atlas to have produced B papers, in principle, it's trivial. You don't need a trigger for that. That's the reason why LHC doesn't need a trigger. LHC-B experiment doesn't really need a trigger because they can, in principle, write every one of those things or analyze them. However, we can't do that because we can't read out at that rate. What we can read out is on the order of 1,000 hertz. That's what we have to come down to. So it turns out the W boson production rate at the LHC with the luminosity that we're running is about 1,000 hertz. So if you just read out every one of the W boson events, you're already at 1,000 hertz. So that's a huge rate. We don't, but if you do that, that's what happens. It turns out that when the W decays, there is a spectrum of the electrons that are coming out, and depending on you can chop off the low energy part of it. So low energy electrons or muons from the W decays we throw away, and the taus we sort of try to keep, but not very well. And the hadronic decays of the W, we usually don't even bother keeping. So that's the kind of things that compromises what is called trigger. So you're throwing away things only that you're interested in. We're interested in keeping high energy electrons and muons. Now, what is high energy and what is low energy is something that I haven't defined. We'll get to that in a minute, okay? Top is basically produced very often because it's a colored particle, and we have colored particles in the interaction. So you get a lot of TT bar production. And it turns out that we make about 10 hertz of them, 10 top TT bar events with a semileptonic decay, at least one semileptonic decay that's produced. That's a lot of data too. And we produce Z bosons also. That's about 1/10 of the W rate. The Higgs is, of course, very rare. You get less than 10 to the 4 detectable Higgs per year, 10 to the 4 all Higgs per year. So within 1,000 hertz, we need to store them. So the things that we want to store for sure are all these things that we haven't discovered yet, and the things that we want to study in great detail. Production of multiple W bosons, multiple Z bosons. Those are the kinds of processes we want to study. So that's where our focus is. How do you keep these while throwing away those? That's the job of the trigger. And you need to do this in the context of this ugly picture. If you just take all the thousands of particles that you got and look at something interesting overlaid on it, you cannot see it in this picture. But it turns out that if you take only the tracks with greater than 25, by the way, the greater than 2 is selected there so that the particles comfortably go through all layers of the silicon detector, and you can measure them quite accurately. So even then you have lots of garbage. However, if you only look at greater than 25 GeV, it cleans up very nicely. And if you take only those tracks which come out of the entire detector and label them in this green color, so those are the 4 muons. And in this particular event, you can actually see that those are almost straight lines. That's because they're high momentum ones, they haven't curved as much. So these are good quality, high momentum muons. And this is a event where Higgs decay to 4 muons, and you see them in the detector. And the full detector event is about a megabyte in size. And as I was saying, the rate is about 32 megahertz. So we want to make sure that we keep these. But the events, when we look at it from the outside, would look like this. And you can't really work with something like this to select this unless you have some sophisticated logic to select those things. And that's what the trigger system is about. So in principle, the decision is simple. I want to keep all the good events and I want to throw away all the bad events. But the operator that you need to apply on the data that comes out of the data is actually quite messy. How do we do that? And we also need to do that. You don't want to build a lot of instruments like this and send data to all of them. First of all, you can't distribute the data. So you need to have one instrument which will take data every 25 nanoseconds and makes the decision within some latency, if you like, within a certain period of time to make this decision. We want one bit out saying this is interesting or this is not interesting. So what is interesting? So that depends on what physics you want to do. So this is a table that I used to show long ago when I was 20 years ago when we started on this. So there are various types of physics that we want to work on. Professor Digge told you all about the standard model physics, right? That's the first thing, electroweak physics. That's what the LHC was primarily built for. And what happens is in these things, we have low PT. By low PT, what I mean is compared to the 13 TeV in the center of mass, we have on the order of 30 GeV or so. It's 30 GeV by 13,000, which you could have in principle in the final state particle, right? So it's low in that sense. But 30 GeV is a lot of energy, as you saw. When you go to 25 GeV, it cleans up the event quite dramatically. So we defined our target of low being about 30 GeV. So if you want to study the Higgs boson or the W or Z bosons, you need about 30 GeV. Well, you have some events with lower than that, but if one of them is lower, suppose it's a Z decaying into mu plus mu minus, if one of them is below 30, the other one is high enough that it will be in the central part of the detector and reconstructed. If you have single particles, 30 GeV is more than enough, and you'll get good acceptance for it. So we want to keep events with 30 GeV electrons or muons. Whereas if you want to study Higgs decay, let's say, to tau tau or BB bar, then it becomes very, very difficult because now you have to look for secondary or tertiary particles, which you need to trigger on if it is leptons. And those are actually very difficult to do. So I have a little color code here. Green is easy to do. Red is a little more difficult to do. So we had to work hard to make this happen. At the time we started the LHC program, we thought there will be new physics at about a TeV or so scale. And we were particularly interested in looking for new physics, which has a lot of color in there. So supersymmetric particles is what we were looking for. And in those cases, there are two things which are interesting. One is that there are lots of final state objects because they're coupled to the standard model at the same strength, at the electroweak scale strength. So you have lots of final state particles, which are standard model particles, and you can W's and Z's and the heavy quarks, they'll show up. So by triggering on multiple things, you can get actually pretty good efficiency for this. So multi-objects triggers are easy. That's why I labeled it as green there. But it turns out supersymmetry had another excellent feature, which is what makes us still love it, although we should be very unhappy with SUSY, which is that it has a potential for including a dark matter candidate, as you probably heard about, at least if you haven't read about it, you should know that. So that's an important thing. That's finding a dark matter candidate because most of the universe seems to be dark. And we need to find if there is a fundamental particle responsible for that. So that requires a little bit more work. In particular, this dark matter candidate, it doesn't interact very much, so it'll escape the detector. It'll be just like a neutrino. We don't see it, so you can't say that you've got a dark matter candidate produced and it went in this direction. All that we know is that we produce everything else, and we know from energy momentum balance in the detector, that something might have gone in that direction. And that's what we call missing ET. And you trigger on missing ET. That's another very difficult thing to trigger on. So that's other thing. And then there are other new physics things. There are all sorts of physics that you can talk about. There is a lot of multi-TeV scale physics, which manifests itself in all sorts of detailed things. You heard today about flavor physics, how nicely it fits in the standard model. But there are some deviations also, he mentioned. And these kinds of indirect observations have indicated pretty high scale for new physics associated with flavor anomalies that have been found so far. So it's probably beyond the reach of that. But it turns out that there are certain aspects of it, like B's of X mixing and rare B decays, that we should be able to find. And for that, we needed to have special dedicated triggers. It turns out that CMS detector had special triggers for dimuons. And we were able to do that because we had basically a heavy detector with lots of steel on it. You know, Atlas detector is more than twice as big as CMS, but CMS is much more dense. So only muons come out. There's neutron background, but muons come out, and you can actually have detector thresholds which are much lower. We had a lot lower backgrounds coming from it. So we were able to get our dimuon thresholds to very low value. So that's the reason why there are more papers on B physics from CMS than from Atlas. Why? So the trigger plays a role in what physics that we do, and you need to focus on that from early days. And there are other things which are easy to do. If you think of some crazy scenarios, then usually triggers are not that difficult to build unless those crazy scenarios involve very low mass jets or something like that. Then this whole thing is out. So this slide is meant to be saying that the trigger is challenging, and the scale that we're talking about is few tens of GeV when compared to 13 TeV in the center of mass. How do we get a selection process done like that? So in order to do that, like everything else, we divide and conquer the problem. One thing that we do, one thing that you see in this picture is that there are two grids, right? And both of them are grids. The grids are meaning to say that we can parallel process. That's a very, very important feature of this. Highly parallel processing. That's what we need to do in order to digest the data quickly. So it turns out that even if you have a very high degree of parallel processing, you need to actually get the data to these systems. So it takes time to get the data to the system. And as a result, you have two different time scales that we could use. So Sergio Chitulin, who makes many of these graphics that CMS has, is like our Leonardo da Vinci. He's from actually the same city as da Vinci is from. So he is really good artist. I think some of you know, so Sunanda knows him. He makes beautiful graphics. So he made this graphic also, although this is not maybe that beautiful. But anyway, the idea is that for amount of processing time we have available, we divide it in two things. This is not just a graphic, it's also a brilliant idea. The previous experiments, we had 3-level systems and very complicated systems, but he observed the technology evolution. This is before the web took off like crazy. And he knew that it's going to take off soon. So he and my colleague at Wisconsin worked together and figured out that the telecommunications technology will improve sufficiently that we'll be able to survive with just 2 levels. So they identified that at some point, if you wait long enough, you'll be able to buy a switch so that you can collect that megabyte of data per event and distribute it in a form of computers. Here they show only a small number of them in the picture, but we have on the order of 12,000 computers that we are distributing the data to. But you can do that only if you have milliseconds of time available. You can buy a switch, commercial switch, because there's so many people who are connecting to the web that you will have to build larger and larger switches. And that was the projection. I knew that this will be an affordable switch if you just waited long enough. It turns out that high energy accelerators always take longer than you originally planned it will take to build. And it turned out we were able to actually buy a switch for a reasonable amount of price, less than what we originally anticipated to distribute the events. But before we do that, we have to reduce the rate further down. And that's what is the level 1 trigger system. And for this one, we built a system using gate arrays, basically. There are two types that you could have. In the early days, we were building these gate arrays as part of our own chips that we designed. Only problem with that is that, actually, there are two problems with that. One is, it is very expensive to produce these ASICs. And you produce the ASIC, if there's an error, it will cost you $100,000 every time you want to fix an error. That's a little much. And it also costs 6 months or so because you need to go back to these vendors and remake them. So ASICs was not a great idea. The other problem is that ASICs cost by how many wafers you produce. In a wafer, you make a lot of chips. If you're making 5 wafers, it will still cost you a huge amount of money, and they're not going to give you the discount. It won't be like simple chips. Each chip is going to cost too much money. So that was the problem that we had, but initially we did make ASICs, basically gate arrays, but it would be nice if we can also make them flexible and programmable. So that's what these field programmable gate arrays are. So we're not the only ones having that problem. It turns out all the switch vendors had the same problem. They had decided we'll work with this particular technology, and then technology evolves, and then they need a different kind of switch. It was very important for them to prototype quickly. So they were interested in FPGAs also. So the FPGA revolution was not driven by particle physicists, it was driven by other people, but we benefited from it. So we converted everything from ASICs to FPGAs. So I'll only describe the system with FPGAs. The original system that was used to find the Higgs is based on ASICs, but some of them were FPGAs also, but now it is completely FPGA-based system. So we'll talk about that. There, the timescales for processing are on the order of, a tenth of a microsecond or something like that. I say a microsecond there, but you'll see what I mean by that in a minute. Okay. So what are we doing? We just gave up completely on getting the data from the tracking detectors. We decided that we'll leave the, I'll describe using this slide instead of the other one. So what we decided to do is only read out the calorimeter and the muon system. And we decided to give up on dealing with this particular aspect. You saw this picture in Danielle's slide. So we decided to give this to a later system. That's the second part of the system. Oh, maybe I forgot to say one little thing here in this previous slide. It's important to say that. So each of these boxes is meant to represent a computer like this one, a processor like ordinary Intel processor. Mine has a different chip, but it's a processor. Each of these is an Intel processor, if you like. Here, though, each of these blocks is a field programmable gate array. And some of the field programmable gate arrays are looking at a small fraction of the detector, right? This may be looking at only the muons coming in that particular region. This may be looking at muons coming from another region. Think of this as 8 or 5 space, and you're looking at individual blocks in that area. Okay. So what we decided to do is look at, so this is the calorimeter unfolded. This is a cylindrical thing. So you unfolded it and you got this plane in which there are a lot of crystals, which are these greenish thing. And we made these greenish things align with this red things, which is the hadronic calorimeter. And there are 25 crystals in each of these green blocks, by the way. And what we did is we looked at, we obtained the data in a coarse grain. Some of the 25 crystals energies comes out. And if you happen to have a very high energy photon or an electron, then all the energy is clustered in one place. If you happen to have a jet of particles coming in, it will be distributed over a group of them. So we need to find the sharp clusters versus these broad clusters, if you like. So the broad clusters are jets. The narrow clusters, which are purely electromagnetic, are electrons or photons. You can't tell whether it's an electron or photon because we don't have the track information. You only know electron. You only can separate between narrow clusters and wide clusters. At this time, we thought that measuring taus would be very difficult. So we didn't think about it originally, but we sort of tagged on taus to this by looking at narrow clusters which have both electromagnetic and hadronic energy. A tau primarily 50% of the time decays to a hadronic object. So that will be like this red thing. And it will also have some photons accompanied by that. So if you put those things together, you get a narrow but green and red mixed cluster, if you like. And we had implemented the tau algorithms also. These are very simple algorithms, right? These are simple algorithms, and we're working on reduced data. Instead of taking 25 crystals, we're taking 1 tower compared to that. But still, it turns out that there's 72 by 56 towers. This rectangle is 72 by 56 histogram, two-dimensional histogram, which you need to process. And each of those has got, you need to have energy resolution, at least at the level of distinguishing between few GeV and 10 G, not 10, few GeV and something on the order of 200 GeV. You won't have that kind of dynamic range. So 256-bit, 8-bit energy dynamic range. That's the kind of dynamic range you need for the vertical coordinate, and you need 72 divisions in phi, 56 divisions in eta. That's still a lot of data coming into these processors. It turns out you cannot put all of data into one processor. We had 18 crates worth of electronics originally, which was receiving that data. And now in the operating system right now, we have about 4 crates of electronics that we built processing that data. For the muons, they penetrate and go to the triangular region here is both the tracker and the calorimeter and the solenoid, and it tracks bending like this. And outside of the solenoid, it's bending the other way. What we want to do is measure the curvature here. How do you measure the curvature of the muon as it goes through it? Now, it turns out that it's a huge detector, and we need to take this data. And what we did is that for these chambers, these are gas detectors. I think you already had a lecture about gas detectors. They're very slow compared to silicon detectors or compared to even calorimeters. And what they did is implement these mean timers, as they call them. I don't know if the mean timers were discussed. So the particles drift, and you have a readout on 2 different sides of that. And depending on the time difference between the two, you can say where it has gone, and you can actually have electronics, digital electronics, which will go and compute where the particle has gone in this range in a reasonable amount of time. They're slower, but you can do that. So that's what is done to identify these tracks. Basically, you're looking for coincidences which are within a window. So anything which does not bend very much will have that coincidence. Anything which bends a lot will not have that coincidence if you look only with a narrow vision. And the idea of trigger is to look in the narrow vision and see that if there's a high energy track. If it went to the side, we will miss it, and that's a good thing because low momentum things bend away and we want to lose them. So that's what you do. And then we need to link up. There are four muon stations. You have 4 hits like that, and you can connect them, and now you know what the bend is, so you know what the momentum of the muon is. And that's how we determine the muons. Now, that's something that you can do with electronics, and that's what we have built. Now, if you have more time and you have a general processor, then you can write code to go look for pattern recognition in this very complicated thing, spend a second or so on a fast computer, and you will be able to reconstruct all the tracks about something. So this requires digesting a megabyte of data. So we reduce the data from this to this by a long shot, right? We throw away about, the output of this is at the level of 100 kilohertz, 100,000 events per second, as opposed to 32 million per second. We got 100,000 per second coming out of this. Once you get the data rate down to that level, then you can use the high level trigger using ordinary processors, give it more time. And what we did there, to go back here, is that we gave a lot more time for processing for this. We gave it almost, this is 10 to the 0 seconds. So that's 1 second, right? So we gave it a second of time on the CPU to process and digest the event and produce the output. But you can do that provided you have 10,000 of these things. So you have a large 100 kilohertz, right? 100,000 events are coming every second. If every one of them takes a second to process, we didn't have enough but most of them don't take that long to process, so you can throw them away. So we built the size of the form to be sufficient to do this. But it turned out that the switch that we purchased in CMS and similarly in Atlas is large enough to accommodate large number of processors, and that's what allowed us to do this type of analysis, identify all types of particles that were produced within the time scales that we wanted, with a latency of about microsecond for the E gamma and the muons, right? And jets, if you like. Those were found within a microsecond latency, and the 100,000 of those events were sent to the next level, and you had plenty of time to find if the event is interesting and write it down. So I finished the description of the trigger and data acquisition second time in a little bit more detail. Now we'll go dig into the depth. I don't know how much time I have left. Okay, so what we'll do is follow a little bit detailed example of how it will work. This is the first example that I have is just from a textbook example. So literally taken from a textbook, okay, this image. So suppose you have a detector, and at the end of the day, it's a detector which is detecting optical visible light. And the visible light, that's this detector, right? In order to do that, some high energy particle comes in and scintillates in the plastic or crystal in our case, and you get some light, visible light, or maybe near UV, and you put a photocathode, cesium dope, whatever, right? It's a low work function thing, and it will emit electrons there. Those electrons, then you can put it in, basically electron multiplier, just have high voltage, so just get a large number of electrons coming out. Out of that comes a signal, and the signal looks like that. What would be the time of this? So how big would this pulse be if I were to draw a scale? Anybody want to venture? Few nanoseconds. That's what it will be, right? Few nanoseconds. If you have few nanoseconds, you can build electronics in the old electronics. This is how the electronics for my experiment was done in NIM electronics. If you have 100 channels, you can buy this. Each module used to cost $1,000 in those days. A module accepted 16 channels. It's going to be super expensive to build 10 to the 8 channel system with those $1,000 for 16 channel boards, right? But that's how we did our experiment. So the simplest thing that you can do is integrate the amount of energy with the amount of voltage, if you like, area under this curve, integrate it and put a threshold on it, so some programmable threshold. And if this integral is greater than this threshold, you send a pulse, otherwise don't send a pulse out. That's one channel trigger system, right? You can have a system like this that is built and it will just sing on its own. You'll get these things. Whenever you get this, suppose you do two things. You take the output of this and have divided in two parts. One part comes out here, it's just sitting there, and another part goes through this. And whenever you have a pulse, you digitize it and make it into an 8-bit number and send it out. That's your data acquisition system. That's the kind of systems that we used to build, the early counter detectors a while ago. You probably heard about counters versus plates, photographic plates on which physics was done, where things were taken. Right? Yesterday in Sridhar's lecture about history of particle physics in India. History of particle physics in India is the same thing as history of particle physics everywhere in the world. So that's what that is. So to go a teeny bit deeper, I have a detector and detector plus sensor. So I put the photomultiplier also in there. Typically you amplify it, and then you actually filter that data and you shape the data. There are lots of parts to this thing, and then you sample the thing so you can make a digital signal out of it, which has got some bins. So basically made this into a histogram in a time window, horizontal axis is time, and you have a histogram. And then you can use a filter to remove garbage which is coming through. You have some stray pulses which will hit, and you need to get rid of them to get to a lowest level. Maybe you want to do some zero suppression, right? So Danielle talked about this neutron background. Well, there's neutron background in the muon detectors. There's some neutron background in the calorimeter also. And there's a lot of low energy photons which are coming from neutrons hitting materials and all sorts of things. Sunanda will tell you more about all of this detail, I think, maybe not. But there's a lot of background which comes. There'll be stray random pulses all over. You want to get rid of that. You do zero suppression. You also have electronics noise, but you need to get rid of. So you need zero suppression for that as well. On top of it, you may not have the dynamic range that you want for the trigger system very easily. I told you earlier, 8 bits may be okay. But typically for offline measurements, if you want to get Higgs to gamma gamma mass resolution very well, you probably want a 12-bit readout. But that's about 50% more bandwidth, which we want to conserve in a trigger system. So we have to do some range compression to have the dynamic range, but maybe at the very high energy, you don't need the resolution. We're saying that you have greater than 30 GeV particle. You don't need to say that it is 53.2 GeV. We don't need to say that. We only need to say that it's greater than 30. So you can sort of flatten out the high energy range of it. So that's the range compression. And then you need to store this data while you're making the trigger decision. You store all the detailed data and you make the range compressed data logic. And then once you have that pulse, which says select event, like what we had in the previous page, this one, when that pulse comes out, instead of that pulse coming from a simple logic, we'll have large number of them working together to make a logic. And then you read it out. Once you have the readout, then you can do more interesting things, which we do actually in our calorimeter. So I'll show the implementation of this type of step for the eCal that we built in for CMS, if you like, in a minute. And then you format it and read out. And this is where that mega switch that we bought from a company comes into play. And there are thousands such channels in the detector, just from the calorimeter. And for the other things, we don't do this part. We directly take the entire signal out. That's the tracking detector, and all of it adds up to about a megabyte of data. So that's what we do. I think I'll skip this slide because it's also there again. I'll skip this too. So this is the range compression I was talking about. Instead of going full detail, you can do it. So the other thing that happens in detectors is that once you have a big pulse, sometimes there's slow components which will take a long time to decay. So space charge builds up in some detectors. In other detectors, you have a big pulse and it's got 2 time constants. There's a nanosecond level pulses that we're interested in, and there are slow relaxation times in these crystals or scintillators, which will take a long time to go. So there's a baseline that you, and the baseline can drift because of electronics, power supply variations as well. So all sorts of baseline needs to be subtracted off. So that's another thing that you'll have to worry about. It's system is not always stable. So here's a cartoon of what we built for eCal, electromagnetic calorimeter for CMS. It's got various parts to it. That's why I wanted to show this picture. So we have 25 crystals arranged in a 5 by 5, which we are calling a trigger tower. And we want to read out one number from it, an 8-bit number, which says what the energy is for that thing. So what do we need to do? What we do is we take 2 types of data. One type of data is called trigger primitives. That trigger primitive is some of a row of crystals which are added together on the surface of the detector. That's one optical fiber coming out of this. There's another optical fiber. Offline, we want to do detailed analysis. And this one gets data out, but it gets the data out for each crystal separately, all 25 of them. And it also gets all time samples. We digitized it and we read out several time samples, 10 time samples per trigger, it'll read out, right? But it turns out that even that was too much. So we had to build another layer here, which is called selective readout. I'll get to it in just a second. But all of this needs to be orchestrated, and that's a very important aspect. And the thing which orchestrates the whole thing is a clock and control system, which is called CCS here. One thing that you'll learn if you work in trigger system is that there's so many acronyms. Our famous Sergio Chittolin decided he'll have 2-letter acronyms. And then one day he was giving a talk in a CMS meeting, And he got confused because with 2 letters, there were not enough combinations available. He called 2 different aspects of the system by the same 2 letters. So after that, we changed to 3 letters. So you have a 3-letter acronym for everything. There are a lot of 3-letter acronyms for our experiment. They may mean different things for different experiments. So ignore that, but this is the clock and control system. This is called the trigger control card. This CC means control card. This one is clock and control. There's no consistency, okay? So this one drives everything. It provides the 40 megahertz clock. Every 25 nanoseconds, you have a beat. But it turns out that's not enough because the data is transmitted in optical fibers, and we don't have enough optical fibers, enough power to drive all the lasers for these optical fibers if you just use that low rate. So what we do is we time multiplex them into higher bandwidth. So you need clocks which are even finer than this. So it actually distributes a 25 nanosecond clock, but it's accurate to better than a nanosecond. That's what you need in order to split things up. So you take the 40 megahertz clock, phase lock it to it, and divide it into higher frequency clocks. So we built most of the electronics with 160 megahertz or 320 megahertz now using those clocks because modern FPGAs are able to run at very high rate. But the ASICs that we built for the early part of the trigger system were done at 160 megahertz. Now, if you look at the Intel CPU, some of them are running at 800 megahertz, right? But you need to have a sub-micron, very expensive silicon to do that. So anyway, the ones that some of these systems had silicon that was custom built for LSC experiments. So that's what we do. So you got the trigger data, and the trigger data is now put on another fiber and sent to the calorimeter trigger. And the calorimeter trigger finds those clusters and sends summary of that data to a global trigger. And the global trigger digests the information from the calorimeter trigger. This is the EM part, and the HCal part also enters this, and the calorimeter part and the muon part enters this. All of that is digested together. An event with a muon and an electron, that fires a trigger, and you get 1 bit sent out. And now this one is another timing system. What it does is that it distributes the fact that there was an enablement trigger. That needs to go back on this fiber to this. And when that bit is lit, then you read out on this blue fiber the whole thing, and eventually it comes to the DAQ system. So this is just one system with just cartoons. It's already fairly complicated. And this thing fits in about 9 to 10 racks of electronics crates. Yeah, I'll get that. Should be fine. There's one more lecture next tomorrow, so I can do more. So each of those racks has 2 to 3 crates in them. Each of those crates has about 10 to 15 cards. Each of those cards has 1 mega FPGA on it. It's a lot of FPGAs involved in doing this processing. Let me skip that. So this is an important thing. So I talked about parallelization, and that parallelization is very important to solve the problem. So what happens is, there are 2, the picture here is developing like this. This is the time axis, and this has a limit. You can't just go on forever. So the scale, the horizontal scale of this is few microseconds. And the vertical scale going down is the eta phi space, if you like, percentage of detector that is covered. Take a small fraction, 1 trigger tower at a time. That's 1/72 by 56 in the case of CMS for calorimeter. That's a small fraction, right? 1/5000 or so of data. That means that there are about 5,000 of these FPGAs, if you like. All right. So those are processing the signals coming from the detector. And I didn't draw all of them because if I draw all of them, it'll become just black. So there are 5,000 of these kind of things, approximately. And the output of that is tens of thousands of inputs which go into this trigger primitives generators, okay? And because there are several fibers coming from each of them. And time is passing as it goes through this processing. Every clock tick you have to account for. And it turns out there's a reason why these lines are long. because the data takes some time to go from one subsystem to another, one board to the other. They're connected by fibers. Some of those fibers, because I said it's 9 crates or 10 crates, well, the detector is actually many 100 meters away. So there is another long stretch here, which I couldn't draw. So all of that takes time. It takes time to propagate the signal on these fibers. So it takes time. It turns out that out of 3.6 or so microsecond time that we have, almost all of it is taken by, more than 3/4 of it is taken by just signal transmission. So rest of the clock ticks. So if each of these lines that you have, the vertical lines in each block here, is the number of clock ticks that we have to do the processing. So the amount of processing is a lot of additions. You need to find the shape. So how do you do that? You need to go and do some logic to do that. Every logic step adds some time to it. So what we do is multiplex it. As I was saying, we processed at 164 operations are happening every one of those clock ticks to do that. And that's what we did. So first you made the trigger primitives. That was one aspect. You need to find the energy and put it in one bunch crossing. That's what this is showing. So you get a pulse. I just inverted it from the previous shape. And we truncate it. That's what that's doing, filtering. We just remove the baseline and you have something falling like that. You subtract it off and you get that. That's after baseline subtraction and filtering. And then we don't want that many samples for one pulse. We just integrate that, put it in the, we also find the peak time and put the entire energy in one bunch crossing. So that's one 8-bit number that you got. So that's what is trigger primitives generation. So that's happening in this logic. It takes several clock ticks to do that logic. You can do that you have to do that for tens of thousands of inputs. And then you have to do these regional triggers. Regional triggers are finding these little clusters everywhere. But those clusters are in different parts. Sometimes the cluster is shared between two things. So they have to have cross communication between these cards. All those things take time, and that's the time step shown there. Again, it takes time to send that data from this crate to this other crate, which has got a different thing. This one is what we call a global calorimeter trigger or a global muon trigger, which is counting how many muons are above threshold or identifying these are the sorted muons, the highest muon, next highest muon, next highest muon. Sorting is an expensive operation, takes logic. So that's why several time ticks are used in here. And finally, the global trigger guess, here are the top 4 electrons found in the system. Here are the top 4 muons found in the system. And then it takes, here's an event with 2 muons above 10 GeV. That's interesting. Let's keep it. This is an event with 1 muon greater than 45 GeV. Let's keep it. Here's an electron or a photon, we don't know, about 60 GeV. Keep it. Rest of them, throw it. And what it manages to do at the end of this global trigger, that logic again takes something. But this one is covering the entire detector, right? So in the entire detector, we know what the top 4 muons are, what the top 4 electrons are by the time it comes to this, because we have input from each of the segments. And that's what we're doing here in this. So eventually, this L1A will be pulses coming out, and the rate at which that is coming out is 100 kilohertz maximum. If it exceeds 100 kilohertz, what happens is really, really bad. There are buffers in which you store data. If you exceed 100 kilohertz, you won't have time to read all of them. The buffers will get full and the whole system shuts down and you have to call somebody to help fix the problem. And this happens, but not very often. It usually happens only when some detector decides to go bonkers, some electronics channel got stuck and is continuously transmitting a very large energy. So you'll have to deal with that. So operations is a big deal. That's where we have a crew of about 10 or 15 people minding this business every week. So CMS calorimeter, as I was saying, if you take the full granularity, you have 81,000 channels in it. But in the trigger so far, we reduced it by a factor of 25 to about 5,000 channels and processing it just for the calorimeter trigger. We're identifying these electrons or photons, we're identifying the jets, we're identifying the taus. We're also, since we look at the entire detector, we can also compute missing energy. What's the total energy in the event? And those kinds of things are very useful to decide what the trigger should do. So it's all about channels, channels, channels. I'll close on this slide and take some questions. So presently, For phase one electronics, phase one is after the upgrade. After the Higgs discovery, we upgraded. The reason why we had to upgrade is because we're getting a lot more data per event. The integral amount of data that we still haven't got to the target luminosity of LHC. But instantaneous luminosity is 2.5 times what we originally planned. Because of that, the complication of the trigger has become very high. So we are already upgraded our trigger system 5 years ago. And at that time, this is the rate at which we had. So we had 18 cards with one FPGA on each of them. Each of those FPGAs has about 56 channels, and the data that's coming in is at the level of about 5 gigabit per second, the input data. And then it goes to other cards and so on and so forth. I won't list all of the detail. That's the input for the calorimeter trigger alone. And it takes 18 cards. And to further process this is the regional part. And the global part is another 10 cards. And then there is another 2 cards, each of them with a gigantic FPGA. We'll talk about details of the FPGAs next time with the hardware that it takes to implement this. For the upgrade, what we want to do is read the full granularity. We want to get the crystal level information. In order to get the crystal level information, we're going to use the advances in technology again. So now we can purchase cards, FPGAs, which can take up to 25 gigabit per second input. So we have upgraded from these things internally, they're getting data at this rate, but they're transmitting data at 10 gigabit per second. So from 10 gigabit per second FPGAs, we're going to 25 gigabit per second FPGAs. We're moving from about 70 or so channels to hundreds of channels per FPGA. So the scaling is not as high. And this is something that you observe in telecommunications and computation industry. We're hitting a certain limit in the processing ability, and that has restricted. So the growth in electronics development is there, but not sufficient to keep the number of cards the same. So we are having a slightly larger system. This is just looking at one subsystem, slightly larger system, but more powerful. So that's what the system that we will talk about next time, how it is built and put together.
Okay, thank you, Sridhara.
Right.
Any quick questions?
Yeah.
So can you give a little insight of how these numbers would be in the new upcoming AGCAL?
I did not put AGCAL intentionally. The reason for that, it's not completely well defined. And what we did, another thing that is done is that this is the reason why you notice that I put barrel there intentionally. So the reason is that the AGCAL has so much more data because we start putting silicon detectors in the calorimeter. So the number of channels just grows almost exponentially. So for whatever reason, instead of defining trigger system in our domain, we put some of that electronics in the AGCAL system. And what they're doing is digesting this. So they have 250 or 300 cards with the same FPGAs to reduce the data before it gets to. So the equivalent of this for AGCAL is about 10 times bigger. That's a good way to put it. It's 10 times bigger. I didn't write that because that would be too expensive to talk about here. Yeah, some of it is not totally decided yet, but it's about 10 times as big. Yeah.
Can you go to the slide where you had several abbreviations?
I have a lot of slides with several abbreviations.
Yeah,
this one. Okay.
So you talked that this TCS and TTC sends a signal back to the trigger tower. So can you explain once again what is this?
Yeah, once you actually have the trigger, we want to read out. The blue line is the most important line. That's the thing which is sending the data to acquisition system. You have to trigger that. That means the data is stored on the front end itself. By the way, which is written like a little shown as a little block here, it's actually several little electronics cards. One of those electronics cards has a large memory. In that large memory, we are storing detailed data for each crystal, but we can't read it out. We only want to read it out when we get that trigger me pulse. You need to get that trigger me pulse back to that system. So we use this system to send that trigger me pulse back. So this system needs to get that trigger me pulse back. So the global trigger decides, trigger me, that's this one. This is 1 bit. That bit goes to this distribution system. It gets back to this CCS board, which sends the signal to this system here. And that triggers the blue part of this and sends the data to the DCC. And this one also gets that. Every one of these things, you look at this CCS, it has a line to every one of these things. It doesn't have a line to this because this is just for data suppression, but it has a line to this and it has a line to this. And whenever that comes, that counter tells you, here's an event, read it out. This one knows, I need to read out this event, and it will send it to the next level. And the DAQ system gets thousands of links like that. And it will say that, every one of these things is time-stamped by the trigger. So it will collect all the signals that have come to it at a particular timestamp together and makes a megabyte of data and says, this is the event. So that number, that fact that it triggered needs to be distributed with an ID stamp on it. That's what we call level 1 trigger accept, L1A signal. And that's very, very important that it's the same thing everywhere. So this is just one example, right? There are tens of thousands of those things. It has to be distributed. So these are very large laser systems. So they need to drive thousands of optical fibers with the same signal. Not very interesting, but absolutely critical. And they need to do that with a jitter in the signal at the level of a few tenths of a nanosecond, because all the processing is happening at 160 to 320 megahertz. So you need to have very low jitters so you don't accidentally pick up the wrong fragments and call it one event. Then you'll have bizarre discoveries, right? You'll have large missing ET. We would have found dark matter by now if we didn't do it right.
Okay, I think with that, then thanks Sridhara for today, and tomorrow we will have his next talk. And
Enjoy your lunch.
we'll go for lunch, and before the lunch, there is again small announcement. Some of you want that extra lab, but I did not receive much of the request, so we did not fix anything yet. So if it will start, if you have not filled up that Google Sheet, you filled it, it will start from Friday, because tomorrow evening also we have another lectures. And today again, then now in the lunch, and at 2 o'clock to 6 o'clock, you will have a lab sessions, and then 1 hour is free times. You roam around in the seashore, and then 7 o'clock, the dinner, and then go back to the hostel. Okay.